So far we have dealt with the syllabus of class 11. The last 4 lectures were on wave motion. Now we start with the syllabus of class 12. The first chapter is electric charges and fields, and we take up the topics Coulomb's law and electric field in this lecture. You see, we know that there are 2 kinds of charges, positive and negative. You must have done these experiments in class 8 or 7, that you rub plastic straw with paper to get it charged. You have another straw rubbed with paper, bring them near each other, you will find they repel. On the other hand, if you charge a glass rod rubbed with silk, then the glass rod and the straw, they attract each other. This shows us 2 things. One, that the charges are of 2 kinds. It is convention to call charges acquired by a glass rod rubbed with silk as positive charge. It is just a convention. As a result, charges that appear on straw when rubbed with paper become the charges of the other kind, which is negative charges. These experiments also establish that there is a force of repulsion between like charges. That is, as I told you, if we have 2 straws charged in a similar manner, then they repel each other. So, there is a force of repulsion between charges of the same kind. And what is this force? This force is given by Coulomb's law. For your information, Coulomb was a French scientist, and the law he stated is the following, that the force between 2 charges q1 and q2 placed at a distance r from each other is given by F equal to, this is the magnitude of the force, 1 by 4 pi epsilon 0 q1 q2 by r squared. The force varies as this inverse square of the distance, and it varies as the product of charges q1 and q2. And this quantity 1 by 4 pi epsilon 0 is a constant of proportionality, and epsilon 0 is called the permittivity of free space, strictly speaking permittivity of vacuum. The unit of force is Newton, and the value of epsilon 0 is 8.85 into 10 to the power minus 12 Coulomb square divided by Newton into meter minus 2. And the combination, you see, you will require very often this combination 1 by 4 pi epsilon 0. This combination has the value 9 into 10 to the power 9 n m squared c minus 2. And remember this is the magnitude of the force proportional to the product of charges, inversely proportional to the square of the distance between them, and this is the constant of proportionality. If the charges are kept in a medium of permittivity epsilon, epsilon 0 is the permittivity of vacuum. So, we have another medium which has a permittivity epsilon. Then the magnitude of the force between the 2 charges is given by F in the medium 1 by 4 pi epsilon q1 q2 by r squared, Coulomb's law, which we can write as epsilon 0 by epsilon into 1 by 4 pi epsilon 0 q1 q2 by r squared. And this ratio epsilon by epsilon 0 is denoted by capital K and is called the dielectric constant or permittivity of the medium. You see, this is only the magnitude. We shall see later that the force is actually a vector, how to write in the vector form. But you can see that this comparison of force F is in vacuum, this F is in the medium, and you can see that force in the medium is 1 by k times the force between charges in vacuum. That is, if you go to a medium of dielectric constant k, then the force decreases as 1 by k. Here I give you just a information, dielectric constants of a few common substances, and this is the source. So, common substances: air epsilon 0, dielectric constant sorry K is 1.00059, water K is 80.4, mica between 3 and 6, glass between 5 and 10, and glycerine 42.5. What does it mean? It means that if the force is F in vacuum between two charges kept distance r, then if I keep them in water, same charges, same distance, and the magnitude of the force then is 1 by k times, that is, it is 80 times less than that in vacuum. That is the meaning of dielectric constant. It is important to notice that both the Newton's law and Coulomb's law are inverse square laws. You are familiar with the Newton's law already. However, in the Coulomb's law there is no universal constant. In Coulomb's law we have a constant 1 by 4 epsilon 0. This is not a universal constant, whereas either 1 by 4 pi epsilon 0 or 1 by 4 pi epsilon, these are not, this depends on the medium, this is not a universal constant. Whereas in the Newton's law, capital G is a universal constant. This means that the electrostatic force between charges depends on the medium in which the charges are placed. Moreover, the gravitational force is always attractive, this is important. Gravitational force is always attractive, whereas the force between charges depends on the nature of charges. If the charges are positive or both are negative, then the force is that of repulsion. If the charges are of opposite type, one negative, the other positive, then there is a force of attraction. In gravitational force, because it is of the same type always, cannot be gotten rid of. However, by suitable distribution of charges, the electrostatic force can be removed from a certain region, and this is a very important thing for the theories of the universe. Now, we learned earlier that the gravitational force is a weak force. Remember when we were talking of gravitation in class 11, you remember that I gave you the value of G, which is 10 to the minus 11 or something, and told you that the force of gravitation is very weak. So, let us see how weak it is. So, we are given the charge of electron 1.6 into 10 to the power minus 19 coulomb, charge of proton again 1.6 10 to the power minus 19 coulomb, and 1 by 4 pi epsilon 0 is 9 into 10 to the power minus 19 nm squared c squared, and mass of the electron is 9.11 into 10 to the power minus 31 kilograms. Mass of proton is 1.67 10 to the power minus 27 kilograms, and G is 6.67 10 to the power minus 11 nm squared kilogram minus 2. What we shall do is to find the electrostatic force between a proton and an electron and gravitational force between the electron and the proton and find their ratio. So, we just put in numbers and we find the ratio. F coulomb by F gravitation is 10 to the power 39, huge number. That means, the electrostatic force is something like 10 to the power 39 times stronger than the gravitational force. So, gravitational force is really a very weak force. Imagine now an electron being pulled vertically upward by a proton. You see, proton attracts the electron, so it can pull it up in the vertical direction given in this diagram. At the same time, the electron is pulled towards the earth by a force mg. So, we have to find the distance r, so that the two forces are equal, that is, the proton can hold the electron without being attracted by the earth. So, we just find the force due to Coulomb attraction and then equate that with the weight of the electron, that is 9.11 times 10 to the power minus 31 kilograms into 9.8, and this force is in newtons, both are in newtons. In fact, you equate the two and you can get r equal to 5.08 meters. That is, if I place a proton and electron at a distance of 5 meters roughly, then the electron will not be attracted by the earth, because the force of attraction by the proton balances the force of gravity. Now, I have already told you the force is a vector. Since force is a vector quantity, this equation F must be written properly, so that it reflects the vector character of the force. So, if both the charges are positive or both are negative, the force is repulsive and is given by this formula. The only thing we have added is this r cap. R cap is a unit vector in the direction of r. So, if the two are positive charges or two are negative charges, they repel, therefore, the charges move in this direction, that is in the direction of r. So, r cap. Let us take the 4 cases. Here the two are both are positive. So, the force is along r, the force on this is along minus r. Here both are negative, and again the force on this is in this direction, the force on this due to this is in this direction. Here the two are of opposite sign. So, positive and negative, so attract. So, the force is along the line joining them towards this. If this attracts this, similarly this attracts this, and the force is given by this. If we were to take force exerted on this by this, it would be in this direction. You see, this is according to the Newton's law, that the two forces must be equal and opposite. The force on this is equal and opposite to that force on this due to this charge. We could also define the position of charges q1 and q2 with respect to the origin O of an arbitrary coordinate system. So, this is an arbitrary coordinate system, and r1 is the position vector of q1, r2 is the position vector of q2, r2 minus r1 is a vector in this direction, and now we can write the force, the vector force equal to q1 q2 by 4 pi epsilon 0 into r2 minus r1 divided by the cube of the absolute value of r2 minus r1. See, dimensionally it must remain 1 by r squared. So, this vector divided by the magnitude of the cube of the magnitude of this vector. So, you can see that if we take the force on this due to this, then it is in this direction, force of repulsion, and on this it will be in this direction, again according to the Newton's law. This is the same thing that Newton's law says, that the two forces must be equal and opposite. Suppose that more than two charges are present, a charges q1, q2 and q3, then each one of them interacts with the other two. For example, q2 interacts with q1 and q3, q1 would interact with q2 and q3, q3 would interact with q1 and q2, and like that. However, the interaction between any two charges is such that the presence of other charges can be ignored. That is, if q1, q2, q3, I can ignore this one, I can study the force between them. I can ignore this one, I can study the force between these two, and like that. And then we can, the force between these charges and the force between these charges can be added. They are vectors, therefore, we have to add them vectorially according to the parallelogram law of force. And this principle, that the two forces can be added and you can ignore the presence of other charges, is called the principle of superposition. So, let us illustrate this. So, I now study the forces on q1 due to charges q2, q3, q4 and q5, and you see q2 attracts this charge q1 because both are opposite sign, therefore, the force is in this direction. q3 is also positive, so it attracts q1 along this line. So, these are the two forces, and I find their resultant, they are given by this yellow line. Now, let us bring q4 into picture. q4, they are both negative, and therefore, q4 exerts a force in this direction. So, therefore, I now compound this and this is the parallelogram, and I find this green line is the resultant of forces due to q4, q2 and q3 on q1. Let us now bring q5 into picture. q5 attracts this q1 in this direction. So, the force has this direction, and this now I compound with this green line, and we can find the resultant. So, this blue line is the resultant of all forces acting on q1 due to charges q2, q3, q4 and q5. This is the essence of principle of superposition. While getting the force between them, I forgot about q2, q4 and q5. Similarly, when I talked of q1, q2, then I forgot about q3, q4, q5. So, these are the two forces, I compound them according to the parallelogram law of forces, and that is the principle of superposition. In physics, whenever there is an interaction which gives rise to a force, we explain this interaction in terms of a field. In the case of interaction between electric charges, the field invoked is called electric field. We say that a charge creates around it a region of space or a field and any other charges which stray into this field electrostatic forces. So, if we have a charge creates around it is a space called field, and if any other charge enters this space it gets affected. The field is defined, the intensity of the field or the strength of the field is defined as this. At any point the intensity of the field is defined as the force felt by a unit positive charge when placed at that point. That is, if I have placed a unit positive charge from this charge, then the force felt by this is called the intensity of the field, and the unit of intensity is obviously Newton per coulomb, because it is a force on a unit charge and it is denoted by E vector. So, F vector is given by this, therefore, E vector, the intensity is given by a unit positive charge, force on a unit positive charge, that is F by q2, and if I take q2 from this formula, then I get intensity equal to 1 by 4 pi epsilon 0 q by r squared into r vector unit vector. So, that is the intensity due to a charge q. Q is known as the source charge, and any other charge entering into the field of this charge is called a test charge. Now, what is the direction of the field? Suppose I place a unit positive charge here, what happens? It will be repelled. So, it goes like this, here it goes like this. So, the field of this positive charge is radially outwards. Similarly, the field of this negative charge is radially inwards, because the positive charge will be attracted in this direction. So, therefore, the field of a negative charge is radially inwards. The test charge should not be so large as to affect the field itself. So, the field is defined in this manner, that is, the charge q2 is as small as possible. So, in the limit q2 goes to 0, the electric intensity due to charge q is F by q2, limit q2 going to 0, that is, it is equal to 1 by 4 pi epsilon 0 q by r squared into r cap, as we have done earlier. The intensity of the field decreases as 1 by r squared, like the gravitational field, and like the gravitational field it is a long range field, because the decrease as 1 by r squared is not very strong, is not very fast, and therefore, even at very large distances one can feel the field due to the charges, and therefore, it is called a long range force. In general, a principle of measurement is that the measuring device should disturb the quantity to be measured as little as possible. That is why we said this charge q2 must be as small as possible, and we had limit q2 going to 0. This is a general principle, and you can reason out why the resistance of a voltmeter is very high and the resistance of a ammeter is very low. We will come to that later also. Now, since we have superposition for Coulomb forces, it is obvious that we shall have principle of superposition for the fields also, electric fields. So, if E1, E2, E3 are fields due to different charges on a given charge, then the intensity of the total all the fields together is E1 plus E2 plus E3, and this E in general is 1 by 4 pi epsilon 0 sum over I of Qi by Ri squared into Ri cap. If the number of charges is large, and then we have a continuous distribution of charges. So, suppose we have a volume distribution of charges, that is, we have a sphere or some other body in which the charges are uniformly distributed, and suppose the density of charge, that is charge per unit volume, is rho. Then what happens? In a small volume dV, the charge is rho dV, that takes the place of q, and therefore, the intensity due to this volume element is 1 by 4 pi epsilon 0 rho dV by r squared into r cap. And now, we can integrate this over the whole volume, and we get the intensity due to a continuous distribution of charges. If rho is uniform, then rho can be taken out and we can integrate over the volume. Let us take an example just to fix the ideas. Two identical balls, each of mass m and carrying a charge q, are suspended by massless insulating strings, each of length L. You see, we suspend them by 2, and since they repel each other, therefore, they settle at this position. At equilibrium, each ball makes an angle theta with the vertical, this angle theta. Find the distance between the balls at equilibrium. So, we have to find r. So, what we do? The Coulomb force is in this direction and the tension is this, and therefore, I can take the component of tension along this and the tension along this. This T sin theta would cancel because the charges are in equilibrium, it will cancel this. These two I will balance and these two I will balance. And since there is no other force in this direction, T cos theta is simply equal to mg. At T sin theta, there is no other force, is equal to 1 by 4 pi epsilon 0 q square by r square. I will equate these two, and from this I shall get the distance r. It is simple matter. T sin theta is equal to this, T cos theta is equal to this mg. So, divide one by the other, then we will get r by 2l would be dividing the 2 and using tan theta equal to r by 2l. Tan theta is r by 2 by l, that is r by 2l. So, tan theta is r by 2l. So, when I divide by the other, I will get tan theta, which is r by 2l. This is equal to q squared by this, and from this I can get r, and r is given by 2l q square divided by this. Remember that r, the distance between them is proportional to the cube root of L, cube root of L. This is a very general problem, and this tells you how to take account of the two forces in this case, the Coulomb force and the force due to tension. So, in this lecture we have talked of the kinds of charges, the forces between them, the field of a charge, and so on. In the next lecture we shall talk of the lines of force, which is a very important concept which maps the field of a charge.